Welcome to the series on computer science, and as a part of this series today we will be doing a course on artificial intelligence, and in this course, in this module we will be seeing on informed search, where in the specifically we will be seeing on the A star search, and last module we saw greedy best first search. As a continuation of that, this module is about A star. Now, again a quick revision on the evaluation function, and this is a book example where we see on the right a map of a part of map of Romania, and the evaluation function on the left is given as g of n plus h of n, and g of n is going to be the actual value and h is the heuristic value, and f stands for the evaluation function. Now, if you see on the right, we have a part of the map I said, and suppose we assume this state starting with S as the start state, and the end state or the goal is starting with Bucharest, say B. Let us see how greedy best first will work in this fashion. Assume that the heuristic value of different cities, S stands for the city, F stands for Figueres, R stands for the city, P stands for the city, and B stands for Bucharest. So, let us mark the heuristic value above the nodes. This is 253 and F is 176, R is 193, P is 100 and B is actually 0. Heuristic cost for the goal is always 0. Why? Because at the goal, if we estimate the goal cost, it is 0, while at the start the straight line distance from S to Bucharest, it is 256. Okay. Now, for this graph, suppose if we use greedy best first, I said in the last module that greedy best first we are going to evaluate f of n is equal to h of n, only based on h of n we will evaluate. So, let us say we are starting as S. From S there are two branches, one is R, another one is F, and at S we have the heuristic value of 253. Now, with R it is 193 and with F it is 176. The lowest cost, again it is the priority queue, this is 176. So, branch out, we have B with a cost 0. Now, if we add this actual cost 99 plus 211, okay, this would be some value, and if you take this value 80 plus 99 plus 97 plus 101, this is actually less than 99 plus 211. Okay. Although this is going to be the result of greedy, it is not optimal, but the optimal value is this path, where in this session we will see how to arrive at this path, the optimal one. So, in that direction we will go. Now, again this is a map of Romania, which is again from the book, where we will be using the actual cost, which is the edge cost. This is the g of n value, and this is the straight line distance, which is the h of n value towards the right, and using both we will arrive at f of n value, which is the evaluation function. But before we get into this part of the graph, let us work out a simple representation of a graph. This is very similar to the diagram that I used for greedy best first search. In fact, the very same values we had for the heuristic values for the greedy best first, except that for the edges I have added actual cost. Suppose if you see from S to A, the actual cost is 5, from S to C the actual cost is 6, from S to D the actual cost is 4. So, whatever marked in red it is the actual cost, it is G of n, and whatever marked in blue, this is going to be the, which is near the nodes, this is the H of n. So, H of n, I can say that H of n for S is 7, the same value that I gave for greedy best first search. Now, the step 1, it remains the same, very similar to that of greedy best first, where in step 1 we initialize the node. So, the first would be initialize node, add neighbors, and apart from that we are going to add the edge cost for A star. Now, once the program starts, when we are going to write the program, if you assume we are going to start, this is again the start stage and this is the goal stage for this graph. So, we are starting at S, calculate f of s. Now, this f of s is going to have two factors, the edge cost as well as the heuristic value. This is going to be the major difference between this method and A star and also the uniform cost. So, calculate f of s. Now, the open list will be the same as that we talked in greedy best first. In the open list, remember we will have first the value of the heuristic and then the name of the node, that is the structure we had in the code. So, we will also follow the same thing. So, at S the value is 0, this is the starting stage. At S the value at it which start with G is 0, this is G value, and parent of S it is none. So, initially we had the library of came from. So, here we will maintain a library or a dictionary of parent where S if none, and we will append iteration after iteration. So, this is the initializing portion. Now, coming to step 1. In step 1 we started at S. So, we are going to expand S, and when we expand S there are 3 neighbors A, C and D. So, we will have A, C and D. Now, calculate f of s for neighbors. So, f of s is going to be g of f of s, or in this case f of a, g of a plus h of a. For g of a, this is g of a value is 5 plus h of a is 11 6. So, totally f of a is going to get the value of 11. So, this 11 is the value for a. So, this will have 11 that comes from say 5 plus this 6. Similarly, for C, f of C will have the g value as 6 plus h value as 6, that would be 12. So, this would be 6 plus 6 which is 12, and f of D is 4 plus the heuristic value is 3, which is going to be 7. So, this is the open list that is being given here, 11 comma A, 12 comma C, this is here, and 7 comma D. These are listed in the open list. Now, the parent of A is S, the parent of C is S, and parent of D is S, that is given here in the parent dictionary. So, this is step 1. Now, after this step, if we see use a priority queue, and if we use the priority queue, we can see that this D is the minimal value, this is the minimum value. So, D has to be popped out. The same criteria of the priority queue that we had in greedy best first works also here, where the minimum value is at the front of the queue where it is getting popped. Now, we saw this earlier, this is step 1 that we saw. So, the open list I set this is the minimum value. So, it's popped and immediately checks for goal. It is not goal, and remember we had S, A, C and D. D has the minimum value of 7, C has a minimum value of 12, C has 12 and A has 11. Here, this is the G of n value. Now, D has to be popped out. If D has to be popped out, the neighbor is B. Now, for B we have to calculate f of B. F of B is G of B plus H of B. Now, G of B, if we see, it is going to be is 14 B. If you see from S to D, this is 4, and from D to B it is 8. So, 8 plus 4 or 4 plus 8, I have just inversed this, 8 plus 4 or 4 plus 8 is the same. So, 12 plus the heuristic cost here 2, that becomes 14. This G of B value is 12 plus H of B value is 2, therefore, it is 14. So, this 14 gets updated into this open list. Now, the updated open list, you see here 11 is the least cost. See here we have the branch cost as 14, C has 12 and A has 11. In the priority queue, now A has the least cost. So, at the next stage this has to be popped out, not this. So, this will be popped out. So, if A 11, this will be popped out, again it is checking for goal. Suppose if I redraw the entire one, this will be A, C, D and B. Now, if it is A, it is going to be from A, we are going to branch out B. From A, the branching out is B. The G of B, now we have to calculate G of B plus H of B, that will be for f of B. So, G of B will be from S to A it is 5 and from A to B it is 3. So, 5 plus 3 it is 8 plus H of n value which is 2, it is going to be 10. So, this is going to have a value of 10. So, that is how this 10 gets updated into this open list B with the value f of n value of 10. Now, the parent will be say appending this B's information with A. This was the earlier information of the parent. Now, once the neighbor of is found, this is getting appended into this data structure which is the parent. In the next step, and this is the step 3 which is from the previous one. So, we had S, A, C, D, then D we went to B, B it is not there. So, again A, now we have B, we are at this stage B. The neighbors, this is the third step, and we saw that B with a value of 10. Now, it will check for goal, it is not for goal. So, expand B and then it will reach G, and when we calculate G, f of G, so the path is going to be S to A to B and B to G, S to A to B and B to G. In this case, this is going to be 5, here it is 3 and here it is 1. So, the cost here is going to be 9 and at the goal the heuristic value is 0. So, totally it is 9 plus 0. F of g will be g of g plus h of g, where g of g is 9 and heuristic value is 0. So, this value will get appended in this open list, and since this is minimal, this will come to the front, that the priority queue with the minimum cost will be at the front, and so that is getting popped out in the next round. Now, as an addition, after appending we are adding this b, whatever we visited as b along with the neighbors, that gets appended as the parent with g to b. In the next step, we already saw in step 4 that if we expand b, the neighbor is g with the minimal cost as 9 comma g, where 9 is the f of g value and this is minimal, and since this is minimal, this is going to be popped out, and when it gets popped out it checks for goal. Now, if we draw the graph, it would be S, A, C and D, and from D we went to B. B it is not minimal. So, we branched out A, we went to B and then G. So, this is actually the path that we are seeing. Now, once this is getting popped out, it is checked for goal, and yes, there is a goal, G is actually the goal. So, it gets to the parent node, and from the parent node the list gets constructed as G, G to B. So, G B, then B to A, so A, and A to S, so S. So, this is a path. Now, if we reverse this, the path will be S, A, B and G, which is this path S, A, B and G. So, this is a path with the cost as 5 plus 3 plus 1, which is the 9. In other route, it would be actually 4 plus 8 plus 1, 13, which is not optimal. So, this is the working of A star algorithm, where we are at each step we are going to calculate f of s value. Here s is equal to n, okay, f of n value, where we had addition of g of n value, which is the actual cost, plus the heuristic value h of n. Okay. And now, we will see the say we will apply the algorithm of A star on the map of Romania, where we will see the same problem of starting at Arad and ending at Bucharest, and these are going to be the actual cost g of n values, and the heuristic value is given on the sides. Now, at each stage, first if we see Arad, we start from here, and at this stage this is the g of n value and this is the h of n value. Now, at the next stage there are 3 branches that are coming out, one towards S, one towards T, another towards Z. So, at each stage we are finding out the g of n plus h of n value. See, at each stage 140 is the straight it is the actual cost from R to the state with S, it is 140, that 140 is added here, and if you see on the right side the h of n value for S, this is 253, this is added here. So, g of n plus h of n is going to be the f of n value for S, and similarly for T we have 118, which is this cost, this is g of T, and h of T value is 329, which is got from here. So, this is 447, and similarly for the third place we have 449. The minimum one from all the three is going to be the state start with S, which is this portion. So, we will branch out S. So, when we branch out S, we have four branches, one over here, I will put here this side, here, here and Arad. So, S to A, this is 140 plus, so see, remember how we are calculating, this is 140 and this is again 140. So, 140 plus 140 makes 280, and this 366 comes from this. And similarly, the second place that starts with F, it has from Arad to this place it is 140, and from 140 from S to F it is 99. So, 140 plus 99 makes 239, which is right here. 239 plus this 176, this is h of n value, this comes from 176 here. So, if we go through that, if here we have 646, 415, 671 and 413, also we have 447 and 449. Remember, we are using a priority queue. So, all these values will be remaining in the open list. Now, the minimal one is RV. So, we will branch out this, and in the similar way if we calculate using a g of n value, suppose if we have Arad to Cebu is 140 and from S to RV it is 80 and from RV to C it is 146, we will get 366. And for CR where we see this map and we get the h of n value here. So, at this stage we have 526, 417, 553 along with these values. Now, looking at this place is actually at the minimum cost. So, the priority queue will naturally inform that this place should be branched out. But if we see, there is one place which is much less than 417, which is Figueres. So, actually even though this is small, in the priority queue there is already one more value which has the minimum value is F. So, after coming here, so remember we are going from Arad to this place Cebu and then RV, then bit, and then we are finding out Figueres is actually cheaper. So, we are again coming back to F. So, this is the beauty behind A star. The next stage, this F splits where we have S, B, Cravo, where this is going to be the minimal value. Although, see, assume that we have already reached the goal, Bucharest is already the goal, but it is not minimal. In the priority queue, we will have these values 591, 450, 526, 417 and 553. There only this is going to be the minimal. Although this is the goal, this is not minimal. So, this in this stage this place will be branched out, and once this is branched out, if we see at the end this has the lowest cost, which is 418. So, actually the path would be Arad, this is the path Arad, Cebu, RV, PIT and Bucharest. Arad, Cebu, RV, PIT and Bucharest, and this we have the total cost of 418. And if you remember, this is through A star search. if you remember through greedy best first, we have the value as 450. So, we can say that this is going to be the optimal, and the reason is we are using both the actual cost as well as the heuristic cost in order to find A star algorithm. Okay. Now, coming to the performance measure, is A star complete? Yes, it is complete for finite number of nodes, and similar to that of breadth first search, the space complexity is b power d and time complexity is b power d, where b is the branching factor and d is the maximum depth. And is it optimal? Of course, A star is always optimal. So, before we go to the next module, here is a short question for you to work out, which we can discuss the answer in the next session. So, the question goes like this: you are helping a small delivery robot to find the shortest path from warehouse W to the customer's house H. So, this is a graph where you have W and H. The robot needs to navigate through the city using various roads. Assume these are the roads with different travel cost. The robot also has a heuristic value, where I have listed the heuristic value here. So, for this graph, your job is to find the path to greedy best first and also through A star. So, the answers for this we will be discussing in the next session, and in the next session it will be a continuation, but before that it is a summary of this session. We looked at the evaluation function g of n plus h of n, where the A star works with the f of n value that has the actual cost and the heuristic one. For uniform cost search, if you remember, h of n is going to be 0, and for the greedy best first search, g of n is equal to 0, and for A star we calculated both. So, that is the summary of this session, and in the next session we will be dealing with the local search algorithm, which is the hill climbing, where we will talk only about the neighbors, and one basic aspect is from the start to the end we will not be worrying about how to reach the goal, but provided that we can just reach as such, we will not worried about the path as such. Okay. So, till then